Many railway enthusiasts are fascinated by the performance characteristics of railway vehicles, whether it's the maximum speed, tractive effort, or acceleration capability. Maximum speed is often the most accessible metric, as it is expressed in a straightforward numerical value, how many kilometers per hour a train can reach. In this article, we will revisit the history of railway speed records, focusing primarily on developments since the 20th century. To begin, let us look at records from Japan, which are more familiar to many readers. Due to the inherent instability of tall vehicles operating on narrow-gauge tracks, achieving speeds over 100 km per hour was once considered a significant challenge. Nevertheless, in 1935, Showa 10, the Class 42,000 gasoline railcar recorded a speed of 108 km per hour. This run was essentially a demonstration of the railcar's excellence, staged as a promotional event where numerous invited guests rode the train as it chased the limited express Tsubame. It was a generous and optimistic era, where such public showcases were common. Although speed trials were suspended during wartime, testing resumed quickly. By 1947, Showa 22, the Moha 52 series EMUs achieved a speed of 119 km per hour. This test was not aimed at pushing the limits of vehicle performance, but rather at investigating the speed characteristics of the overhead catenary system. 2 years later, the newly introduced 80 series EMUs reached 123 km per hour, signaling the dawn of the EMU era. Steam locomotives, however, did not quietly fade into the background. In 1949, Showa 24, the C62 steam locomotive set a domestic record of 129 km per hour. That said, the primary objective of this test was not to determine the C62's performance limits, but to assess the structural integrity of a railway bridge. Although the test was conducted with a single locomotive, it involved climbing a gradient toward an embankment within a limited distance. It was said that, given a flat and sufficiently long stretch of track, the C62 could theoretically exceed 140 km per hour, making this trial somewhat bittersweet. In 1955, Showa 30, the 80 series EMUs updated the record to 125 km per hour. At the time, a major debate was underway: would future high-speed trains be hauled by locomotives or operate as EMUs? Faced with the rapid rise of EMUs, the locomotive camp responded assertively. That same year, the EF58 locomotive hauled 4 passenger cars at a speed of 121.7 km per hour. Additionally, the EH10 was modified with high-speed traction motors and a revised gear ratio, achieving 124 km per hour. In terms of speed, neither side conceded superiority. However, in 1957, Showa 32, Odakyu's lightweight articulated EMUs, the SE cars, recorded a speed of 145 km per hour, decisively surpassing the locomotive group. This test, too, was conducted with many invited guests on board. It was a bold trial that pushed the limits of both vehicle and track infrastructure, something unimaginable today, given that general passengers were allowed to ride during such high-speed testing. Not to be outdone, Japanese National Railways, JNR, developed a new generation of EMUs known as high-performance EMUs. In the same year, the Moha 90, originally designed as a commuter-type EMU, was modified with a revised gear ratio and achieved a speed of 135 km per hour. This high-speed run, performed with a flat-faced front-end design, seemed to mock the streamlined styling trend that had begun before the war. It became a matter of national pride, a symbolic contest against private railways and their achievements. That said, JNR's Railway Technical Research Institute had actively contributed to the development of Odakyu's SE cars, suggesting a notable gap in mindset between the technical and administrative divisions within JNR. Then, in 1959, Showa 34. The 151 series EMUs recorded a speed of 163 km per hour. Although this was achieved on a gentle downhill gradient over a limited section, it nonetheless provided strong confidence for the eventual realization of the Shinkansen. The numerous high-speed trials conducted during this period were all aimed at exploring the limits of railway technology, whether EMUs or locomotive-hauled trains could sustain a cruising speed of 200 km per hour. The final milestone in this phase was set in 1960, Showa 35, when the overhead wire test car Kuemoya 98000 reached 175 km per hour. With this, Japan's high-speed research shifted toward the Shinkansen, and on conventional lines, the goal of achieving a commercial speed of 120 km per hour was temporarily fulfilled. At this level, EMUs had ample performance margin, eliminating the need for further high-speed vehicle development, and speed trials came to a halt. Later, efforts were made to raise the maximum speed to 130 km per hour, but again, this remained well within the comfortable operating range of EMUs. Meanwhile, the 181 series diesel limited express trains had entered service, and at these speeds, they already possessed sufficient performance without requiring dedicated high-speed trials. Despite having surplus capacity in the high-speed range, the 181 series, unlike EMUs, were constrained by strict rotational speed limits of a diesel engine. Even if subjected to high-speed testing, diesel trains could not match the records set by the 151 series EMUs. To prevent mechanical damage, the engine was designed not to exceed 2,400 RPM. Unless the wheels were in pristine condition and the engine operated at its absolute limit, speeds exceeding 160 km per hour were unattainable. What if the gear ratio were changed? With a maximum continuous RPM of 2000 and a reduced gear ratio of 1.63, speeds of approximately 190 km per hour could be achieved, as shown in the diagram. However, under this configuration, the train would struggle to reach 115 km per hour on a 10 per mile gradient and would not even engage the direct drive stage. Such a setup would be impractical for commercial service, and modifying the train solely for high-speed trials would be considered frivolous. Incidentally, modern diesel railcars with over 900 horsepower per vehicle offer significantly better acceleration than the 181 series. Yet, in terms of maximum permissible speed, they show little improvement. Again, engine RPM limitations prevent higher speeds. Even though adjusting the gear ratio could theoretically allow speeds around 210 km per hour, the need to draw power for heating and cooling from the prime mover results in poor speed performance despite high output. During this period, there was a growing trend toward adopting gas turbine-powered vehicles, which offered substantial surplus in output. Although a bench test recorded a speed of 153 km per hour for a gas turbine train, no actual high-speed trials were conducted. Similar to EMUs, gas turbine vehicles had more than enough power for conventional line speeds, making full-scale speed testing unnecessary. Even the Kiha 391 series did not undergo dedicated high-speed trials. Despite the enthusiasm for speed enhancement at the time, the emergence of high-performance internal combustion vehicles did not lead to corresponding test runs. Thus began a long hiatus in high-speed testing. Toward the end of the JNR era, however, these trials were revived. Faced with the looming threat of privatization, JNR finally awakened as an organization and renewed its focus on high-speed operation on conventional lines as a survival strategy. With expressways being rapidly constructed and Shinkansen expansion progressing slowly, waiting was no longer an option. To maintain a competitive edge over automobiles, a maximum speed of around 160 km per hour was deemed necessary. This speed pushed the limits of existing EMU systems, prompting renewed performance testing involving track, rolling stock, and electrical infrastructure. In 1985, Showa 60 speed trials were conducted on the Kozai line using the 381 series EMUs, which recorded 179.5 km per hour, finally surpassing the record set by the Kuonoya 93. Meanwhile, demand for higher speeds on non-electrified lines also intensified. With gas turbine development stalled, attention returned to high-speed diesel multiple units. In a sense, this marked the first true high-speed trial of internal combustion railcars since the pre-war gasoline-powered units. In 1986, Showa 61, a modified 183 series DMU recorded 146.9 km per hour, followed by an upgraded version reaching 153.5 km per hour the next year. These tests were conducted in Hokkaido, where Shinkansen development remained uncertain, to determine whether 160 km per hour operation could be achieved with diesel traction. To verify stability and current collection characteristics at 160 km per hour, the gear ratio of the 221 series EMUs was modified, and trials were conducted on the Kozai line in 1990, Heisei 2. Even Shikoku, long considered distant from high-speed testing, joined the effort. In 1992, Heisei 4, speed trials were conducted using the prototype 8000 series EMUs, electronically controlled AC vehicles, recording 158.9 km per hour. Like Hokkaido, Shikoku's challenge stemmed from the lack of prospects for Shinkansen development. These trials led to the introduction of commercial operations exceeding 130 km per hour, though only on a limited number of lines. Despite the initial burst of high-speed development following privatization, it did not evolve into a widespread transformation. JR Shikoku, which even experimented with 160 km per hour operation and rail brakes, found itself constrained by financial difficulties, with fleet renewal being the most it could manage. JR Hokkaido, once hopeful for high-speed diesel traction, saw its ambitions fade rapidly due to various operational troubles. Thus, the push for high-speed operation on conventional lines reached its ceiling. Would 160 km per hour operation be effective on Shikoku's routes? Simulations using the 8000 series between Takamatsu and Matsuyama suggest that, given the need to pass through turnouts at 100 km per hour, there are very few sections where 160 km per hour could actually be achieved. If turnouts are passable at 130 km per hour, certain sections can reach 160 km per hour, resulting in a travel time reduction of approximately 10 minutes. On the other hand, when simulating the Hakodate-Sapporo route in Hokkaido, which features long interstation distances and many straight segments, numerous zones emerge where 160 km per hour operation is feasible. If turnouts are passable at 130 km per hour, the number of such zones increases, yielding a measurable effect. Since electrification is not feasible on this line, let's consider trains powered by internal combustion, specifically diesel railcars. At the time, only gas turbine vehicles were viable for such performance, but for the sake of simulation, we'll assume operation by diesel railcars rated at approximately 900 horsepower, designed for 160 km per hour running. As mentioned earlier, the engine itself is capable of exceeding 200 km per hour, and with a high gear ratio suited for 160 km per hour, it can easily handle gradients of 15 per mile at 150 km per hour. In terms of overall acceleration performance, it is roughly on par with the 8000 series EMUs in a 3M4T configuration. Therefore, there is no significant difference in travel time compared to the 8000 series, and if turnout speed restrictions can be relaxed, substantial time savings can be achieved. This period, when 160 km per hour operation on conventional lines was being actively discussed, represented the peak of post-JNR speed enhancement enthusiasm. However, in reality, achieving such speeds without relying on rail brakes or upgrading signal systems was not feasible. Ensuring level crossing safety, track reinforcement, and other infrastructure improvements required massive investment, and the actual time savings were relatively modest, leading to a gradual cooling of the speed-up fervor. Can documents like the one summarized above be easily generated by AI? While high-speed simulation may be beyond current capabilities, extracting speed records should be well within the strengths of AI. Since this involves searching historical data, automating the process could greatly improve efficiency. So I asked the AI to compile a chronological list of conventional line speed records in Japan since 1900. I tried this using Gemini, Copilot, and Grok, within the bounds of free usage. Gemini provided reliable data up to the record of the Kuemoya 93, but many high-speed tests conducted at the time were either unknown or omitted. Beyond that, the results were a string of hallucinations, showcasing the AI's tendency to confidently fabricate plausible-sounding but false information. One curious example was the Kiha 285 listed at 140 km per hour. This likely stems from a misinterpretation of a document stating it could pass a 90 km per hour restricted curve at 140 km per hour, demonstrating how AI may appear to understand the text but actually fails to grasp its meaning. So, how does Copilot fare? This is a rather straightforward result. While the extreme brevity may give the impression of honesty, it also evokes a kind of delusion, as if the high-speed tests of the C62 were conducted in utmost secrecy. Here's how it appears on Grok. It takes considerable time to load content from various sites, and while the overall assessment seems reasonable, the inclusion of design speed suggests a rather shallow understanding. When investigating niche topics like the one discussed here, one often has to rely on materials that are not publicly accessible. For an AI system without access to such sources, inquiries from specialists in obscure domains or enthusiasts with highly specific interests are likely something to be avoided. Would an AI system that requires offerings be capable of providing more specialized answers? I haven't tried any of the more premium AI systems due to lack of time and budget, but as long as the basic information is sourced from publicly available web materials, expectations should remain modest. Incidentally, if you rephrase the query and ask about similar content, the response may change drastically, sometimes resulting in a spectacular array of imaginative speculation. The behavior of AI systems is truly enigmatic. In the world of software development, it's said that AI has accelerated development speed, but recently there have been reports that verifying the AI-generated content consumes significant effort, leading to reduced efficiency. If this is the case in software development, which demands extremely logical thinking, then evaluating the effectiveness of AI utilization in other industries may take quite some time. Even topics like conventional line speed records, which railway enthusiasts would find fascinating, are still very difficult for current AI systems to research. With AI technology advancing so rapidly, when will it finally become practical to use?